This presentation deals with cleaning data before regression analysis is carried out. Before regression analysis is carried out. Yeah. So there are two concepts that one has to remember while cleaning data, and one is a concept of leverage and the other one is a concept of influence. So an observation whose dependent variable value is unusual given its values of the predictor variables, it is called an outlier. An outlier may indicate a peculiarity or may indicate a data entry error or other problems. So outliers are a problem and it affects the consistency of the data. So outliers have to be either removed or moderated before the analysis can be carried out. So an observation with large residuals, an observation whose dependent variable value are unusual given the values of its predictor variables, is called an outlier. There's a concept called leverage. An observation with an extreme value of a predictor variable. So remember, predictor variable is an independent variable. So leverage is a measure of how far an independent variable deviates from its mean. These leverage points can have an effect on the estimates of the regression coefficients, as you can see in this figure. Now, point A is a leverage point in a relationship between y and x because it is a relatively extreme value when it comes to x. Similarly, point B is an extreme value of x. But the difference between A and B is that A is a good, it does not disturb the relationship between y and x and lies within the relationship, where B can influence the relationship by its presence. So these are the two values with leverage points, which are called leverage points. And by a leverage point can influence the result. And we need to remove those outliers using the concept of influence. So the influence point is a bad value. Influence points are bad values. They should be eliminated from the sample. If nothing is wrong with these points, and if they control the model properties, then it is to be found how they affect the regression model in use. So point B affects the model parameter estimates, standard errors, predicted values, summary statistics, etc. So in this relationship, B is an outlier as it's going to affect the relationship which is ideally like true relationship gets influenced by B, whereas the same is not true over here. So how do we calculate influence? Yeah, so the point B affects the model. So here we use the concept of a hat matrix. Now a hat matrix is denoted by X, which is the data, explanatory variable data, into X transpose X inverse into X transpose. So what you should note over here is X transpose X inverse, X transpose X inverse X transpose Y is the predicted value of the B. It is how you calculate the regression coefficients beta. And here you pre-multiply it with X. So to get the hat matrix, you should multiply the X transpose X matrix, pre-multiply it with X and post-multiply it with X transpose. And it gives and has a very important role in identifying the influential observations. So we use this to identify the influential observations. This is because the variance of E, that is the variance of the error, is sigma E, which is the mean square error, into I minus H, where I is an identity matrix with only the diagonal elements having 1, and H is the hat matrix that you derive over here. H is a hat matrix over here. So you'll get in the diagonal element, by virtue of those ones, you will get positive values in the diagonal, and the off-diagonal values will be negative. Now there is a property, summation of all the HIIs, not HIJs, That means if you add up all the diagonal values of the hat matrix, the result will be P, which is the number of parameters of a regression. And in this case, in our case, there are 4 independent variables, so the value of P will be 5. And the mean P will be calculated as P divided by 2, or it can also be calculated as mean H can be calculated as P divided by 2 or H divided by 2. P divided by 2. If HII is greater than 2, that means if you take the individual HIIs in the diagonal elements, if it is greater than twice of the H, it is considered as a leverage point. It is considered as a leverage point. It's considered as a leverage point. So this is the properties. Now I will show you how this works. It should be noted that all leverage points are not influential on the regression coefficients. Therefore, we take recourse to the H matrix. So the hat matrix diagonals examine only the location of the observations in the X space. So we can look at the studentized residuals or the R student in conjunction with the HII. So you should look at these 2 parameters before you decide an outlier. You should look at both the studentized residual and the HII with the HII. So observations with a large HII or the hat diagonal and a large studented residual is likely to be influential. So you must keep this in mind. So the Cook's distance measure is a deletion diagnostic. That is, it measures the influence of ith observation if it is removed from the sample. So we see whether removing it will have an influence on the results or not. So that brings us to this, because we've just mentioned a concept called the studentized residual. There are 3 types of residuals, or in other words, errors. That is a raw residual, this is y minus y hat. Then you have something called as a standardized residual, which is the error divided by mean square error. And then you have what is called as a studentized residual, which he called it the R over there. We call it R. This is called R. I will also call it R. Which is EI divided by sigma into 1 minus HII. Now HII is the element that you derive from the hat matrix. Which you derive from the hat matrix. Now we talked about the Cook's distance. We will delve a little more deeper into that. So the Cook's distance is calculated for identifying influential cases. So the one formula of the Cook's distance is y hat j. I means one value is deleted at a time. So for every observation you will get you'll get I, if you have n observations, you'll get n Cook's distance using this. Every time one value is deleted and is subtracted from the estimated value, the whole square, divided by p, number of parameters, and sigma e squares, which means some square. Where the estimated mean of y, at observation j based on the reduced data set with the observation I deleted. So you delete one variable at a time and then do this calculation and see how the results fare. So P is the number of regression coefficients. Sigma is the estimated variance of the fit, that is mean square error, based on the observations. So this is one way it's calculated. Equivalent formula, and it's a kind of mystery. It's mystery how it works. D is calculated rather easily because this deletion is a very elaborate, very laborious criteria. If you have 100 observations, you have to find 100 regressions with one value deleted each time, and then the D is calculated. Now this is a very laborious process. This is a laborious process, and therefore we take recourse to this. This is much simpler. Now you see the same DI is calculated as 1 by P, where P is the number of parameters in your regression. In our case, it is 5, into student residuals, into this studentized residuals, into this coefficient, squared, studentized residuals squared, that means you square the whole thing, into HI, which is the hat matrix, divided by 1 minus HI. So term, okay, so this is, of course we know this, we arrived from the hat matrix. So this term is big if case 1 is unusual in the x direction. So you get a big value of this, and thereby it identifies an influential variable, because influence is a combination of all of these. So I will show you how this is done using an Excel spreadsheet. Leverage. So leverage HI for the single variable case, also called the diagonal elements of the hat matrix. So this is also called HII. It measures the multivariate distance between the x's for the case I and the average over x's, accounting for the correlation structure. So this is how it's calculated. If there is only one x, then HI is equal to 1 by n into x minus x bar or divided by standard deviation, nothing but normalization of the variable, squared plus 1 by n. Equivalently, it becomes x minus x bar whole squared divided by x minus x bar whole squared plus 1 by n. So leverage is the proportion of the total sums of squares, this is the total sums of squares, of the explanatory variables contributed by the ith case. So you're doing this for each one. So this case has a relatively large leverage. So if you're talking of a point over here, it is completely away from that point. That leverage value becomes very large. So in addition to this, you have two other measures. One is called the DF betas and the other one is DF fits. So these are other than the Cook's distance for identifying influential cases, you have the DF betas and the divots. So DF betas, which indicate that how much the regression coefficient changes if the ith observation were deleted. Such a change is measured in terms of the standard deviation units. So diff beta calculated is Bj minus Bji divided by S squared T Cij, where C is the jth diagonal element of the X transpose X inverse matrix. So you're familiar with that. And Bij's are the regression coefficients computed without the ith observation. And this is the pooled regression, and this is like a deleted criteria. So you just have to know, because computer programs normally give you this, so this is a very laborious process. So large in magnitude values of DF betas, Ji, indicate that the ith observation has considerable influence on the jth regression coefficient. So you could find out this. You do it for each observation versus each variable, and you can find out which variable affects the regression the most. So the rule is large values of DF betas Ji indicates that the ith observation has a considerable influence on the jth regression coefficient. So jth regression coefficient is related to a particular variable. So you can say which variable influences which case influences which variable. The different bits can also be written like this, and it can be rather simplified like Rij root Rj Ri into T divided by 1 minus H again hat matrix. So this is a studentized residual. This is the product of the two residuals. So measures the leverage impact of the ith observation on the B, measures the effect of the large residual. So together it finds out the influence. Where I is the ith R studentized residual, where T is the ith R studentized residual. Now if modulus DF betas is greater than 2 divided by 10, then the ith observation warrants examination. So this is how this DF betas is interpreted. Now coming to the second measure, which is called diffits. So the deleted influence of the ith observation on the predictor or the fitted values can be investigated by using the diagnostics of Belsley, Koo, and Welsh, as DF bits is yi minus y hat. So y, that is for the entire sample. So this is for the entire sample. And this is with one value deleted, you get the estimated value divided by, so this is done for each variable, you can see that, okay, divided by S into H, where I varies 1 to n, where yi is the fitted value of the ith without the use of the ith observation. So what you do is you delete a variable, estimate the function, but predict the value of all the observations. So the denominator is just a standardization, since variance of yi is equal to sigma hi. So this we have discussed it earlier. So the denominator is just a standardization. So it's HII into standard deviation, standard error. So this diffits I is the number of standard deviations at the fitted value y changes of the ith observation is removed. So it tells us to what extent removal of a variable will affect the estimation. So computationally, diffits can be calculated just like we did earlier. It's a very simple, straightforward calculation. It boils down to T divided by HII, which is derived from the hat matrix, divided by 1 minus HII. That's equal to R student into leverage of the ith observation. So this is how it is calculated, where Ti is the R student. So you take the R student, and so you can calculate this directly. It's not as elaborate. It is not as elaborate as it seems over here. Okay? It can be calculated rather simply by just multiplying the R student by HII divided by 1 minus HII, where Ti is a R student value. Thus, diffits is affected by both leverage and prediction error. Besley, Ku and Welsh suggest that any observation for which the diffits value is greater than twice k divided by n, where k is the number of parameters in your regression, is a variable, that it's a case that is likely to have an influence on your regression coefficient. So just to refresh our knowledge of studentized residual for this, how do we use the studentized residual itself for detecting outliers? And this is done for Y detection, that is dependent variable detection. All the methods we discussed here hitherto relate to the independent variables. So now, to detect the outliers in Y, we use the studentized residual, and you can see the studentized residual is calculated as the raw residual divided by standard error of the residual. So the studentized residual, the denominator is obtained by multiplying the mean square over 1 minus hi squared. So it is the raw residual EI divided by R, or the studentized residual, that is sigma. So the different residuals have different variances, and since the HI lies between 0 and 1, those with the largest HI, unusual X's, have the smallest SE of the residuals. Okay, because of this operation. Okay, if you have a large value, this becomes very small. Because if it is 0.8, this 1 minus becomes 0.2. As against if it is 0.1, so this becomes 0.9, and therefore it is it. For outlier detection, use this type of residual, but use ordinary residuals in the standard residual plots. So when you plot it, use the standard residuals, but if you're going to detect it, you must use the this type of residual. Okay, so this is very important. So the rough guidelines of large, what do you mean by large? So DI values near or larger than 1 are good indicators of influential cases. So if you get a DI, that is Cook's distance, greater than 1, they're an indication. But sometimes a DI much larger than the others in the data set is worth looking at. So don't just follow this criteria of being greater than 1. If it is not greater than 1, just look at the DI values for the other data set and see which are the values, which are the Ds which are relatively large. I mean, if all the values are very small and you get a value like 0.8, fine, that could also be an outlier worth examining. So the average of HI is always P by N. That is a hat matrix. Some people suggest using HI greater than 2P by N as large. So you should remember this. You should remember these things, because in future when you use econometrics, the understanding of this is very important, because you'll find yourself groping for the right answer later on. Okay. So based on normality, the studentized residual should be greater than 2. Is considered to be large. So these are some of the good references. So before that, let us go back and just see what are the measures we used earlier. How do we use this? So outlier detection, this helps to identify inferential observations and helps to clarify the course of action. Use them when you suspect inference problems and when graphical display may not be adequate. So one useful set of inferential statistics are the Cook's distance for measuring influence, the leverage for measuring unusualness of X, and the studentized residual for measuring outlierness. So these things should be clearly maintained in your mind. That Cook's distance is for measuring influence. The leverage is a measure of the unusualness of the X or outliers in X. And the studentized residual is useful for measuring outlierness. So, by influential observation mean influential observations are one of several observations whose removal causes a different conclusion in the analysis. So when you're doing serious analytics, when you're doing analysis where the results are going to be actionable, you must be very careful when you drop variables, because very often you find that some variables which are very large, which look like outliers, may actually be the real variables, and be the real observations, and you can't afford to drop them arbitrarily. Two strategies for dealing with the fact that least squares is not resistant. Use an estimating procedure that is more resistant than the least squares, and don't worry about the influence problem. So least squares, use least squares with the strategy defined below. So this is what you would do. This would be the strategy for dealing with influential variables. So do conclusions change when the cases are deleted? Because what you mean is when you have an influential value or an outlier, both in X or Y, you may leave it out. And if it is not going to change the conclusions, proceed with the case included. Study it to see if anything can be learned out of that. So go ahead with the analysis. But if you think it's going to change your results, is there reason to believe the case belongs to a population other than the one investigation? Do you think that it doesn't belong here? It is an outlier. It doesn't belong here. In which case, if the answer is no, if the answer is yes, then omit the case and proceed. So if you think that value is really an abnormal value, like due to a wrong entry, delete it. But if you think no, it is a big value, it is inherently a big value, then you should see, does the case have unusual distance explanatory variable values? Does it have a very, very big independent value? So if the dependent variable value is very high, then check whether the independent variable value is also high. If it is true, omit the case and proceed. Report the conclusions for the reduced range of explanatory variables. So if you think that the value is really extraordinary, it's really unusual, then omit the case. But then when you make the inference, you must make a point to say that these results are tantamount to excluding the one case. Like supposing you're studying with the banks, we're doing some analysis of bank performance. State Bank will always look like an outlier, which it really isn't. It belongs to the same population. But in the interest of getting a better estimate, you may leave out State Bank. So whatever inferences you draw, you must make a mention that these inferences are drawn with State Bank excluded from the data set. If the answer is no, more data is needed to resolve the question. So this is in brief what I wanted to tell you about theory of influence. Now let me show you an example. Using an Excel sheet. Now here I've generated a new set of data. So you have value 20 values of independent variables, 4 explanatory variables, and 1 column for constant. And just like we did earlier, I take the transpose of it, and then here I multiply. You can just see if I click it, it multiplies the. If I click it here, you see it is x transpose x inverse x transpose. X transpose x inverse x. Okay, that's like we did earlier, so I won't repeat. Cancel. Then here I do so x transpose y. Then here this is x transpose. Then here I get the x transpose x inverse, which you're already familiar with. I've taken the inverse of this matrix. And here what I've done is, I've done the final step. That is x transpose x inverse y. Let's see. So x transpose x inverse x transpose y, which gives me the regression coefficients. It gives me the regression coefficients. I've got the regression coefficients. Okay, then these have already been explained to you, so I won't get into the details. So these are my regression coefficients. These are my regression coefficients. Now from the regression coefficients, I will estimate the y hat, the error, and then I get the ANOVA. So the important thing over here is I'm now going to develop the hat matrix. Hat matrix H. I'm going to develop the hat matrix X. So try to recall the formula. The formula is X into X transpose X inverse X transpose. Okay. So now let us just examine. Now X transpose X inverse, we know the middle term. We know X, the dimension of X. The dimension of X is 20 into 5, including the column of ones. Right? So this is X. So I'm going to multiply this with X transpose X inverse, which is 5 by 5, which is here. Which is here. 5 by 5, X transpose X inverse, which is 5 by 5. So just put 5. And that in turn is going to be multiplied with 5 multiplied by 5. I close the bracket, right? And that is going to be multiplied by rate transpose, of course. That is going to be multiplied by X transpose, which is 5 by 20. Going to multiply this with 5 rows into 20 columns. Now let us see if it is compatible. Okay. So these two are compatible. The resultant becomes 20 into 5. Right? Then 20 into 5 into 5, the resultant will be 20 into 20. So we are going to get a 20 into 20 matrix, but we'll have to do it one at a time. So I'm now going to multiply X into X transpose X. So that will become a 20 into 5 into 5 into 5. The resultant will be a 20 into 5. So let me block off a 20 into 5 matrix. 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20. And I'll do a matrix multiplication. M, M, U, L, T. I'll open a bracket. And then I'll multiply X with X transpose X inverse. That is this. Right. Close the bracket. Control Shift Enter, because I told you that when you doing a matrix multiplication, it should be Control Shift Enter, not Enter. So this part is over. So 20 into 5 into 5 gives me a 20 into 5. Now I'm going to multiply it with X transpose, which I have over here. This is X transpose. Okay, so let me see the resultant. So if I multiply this 20 by 5 with the 5 into 20, my resultant matrix is going to be a 20 by 20. So you should be careful while you mark off the columns. So you should have 20 columns, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oops. Sorry. I'll take a little lower. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. And downward 20, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now I'm going to do my final matrix multiplication before I get my hat matrix, which is equal to M, MULT, open a bracket, and I'll go back and check. So it should be this one, which I just got. That is X into X transpose X inverse multiplied by this last term, which is X transpose. So X transpose, I have it at the top. I just copy it down. Okay, close the bracket, Control Shift Enter. Oops, there is an error. I will again try to correct it. Okay, array 1. 20 multiplied by X transpose X inverse. X transpose X, X transpose. Yes. So it has come. So this is my hat matrix. This is my hat matrix. Okay, this is my hat matrix. It's called the hat matrix H. So this is my hat matrix. And I am particularly concerned only with my diagonal elements. Okay. Right? So I can now create with this. I just copy the structure, copy the structure. Okay, just copy this. Then I'll bring it over here. Control V, and I will delete the values. And now I'll create an identity matrix. I'll create an identity matrix. And change the color so then I can identify the matrix. Yeah. Now I'll create an identity matrix. An identity matrix is one with only ones in the diagonal. 1, 1, 1, 1, 1, 1. This is my identity matrix. And from this identity matrix, I call it a matrix I. This is called a matrix I. And from this identity matrix, I will subtract the hat matrix. And I will put a different color. First I'll say no fill, and then I will put a blue fill. Okay. So I've got fill, and I'm going to now subtract yellow. Okay, so I'm going to subtract I minus H. So this first element minus my hat matrix elements. Oh, sorry, I repeated twice. Yeah, that is not required. This is not required. Sorry, this is not required. This is not required, so I will remove it with a no fill, and I will delete the values over there, and then concentrate only on these two. Okay, so I've got an identity matrix, and from the identity matrix I'm going to subtract. So it is I minus hat matrix, I minus the hat matrix coefficients. Okay, so you can get that, and then I can just copy it till the end, and I'll copy it to the bottom and use a control R and a control D, and I've got, you'll notice that all the diagonal elements are positive and all the odd diagonal elements are negative. Hello? Hello, I'm very busy. Yeah? Yeah. Okay. Oh, I hope you were not in vibration mode yourself. Huh? Yeah. No. Can I call you after 10 minutes? I'm just doing a recording. Can I just finish it and call you? I'm just doing I'll just call you. I'll just finish a recording. I'm in the midst of a recording. I'll just record. Yeah. So now you have got the I minus A. And what you should notice over here is all the coefficients are less than this thing. So the values that we are specifically interested in is the HII, which is the diagonal elements. HII. So let me just get you the diagonal elements. So this is the first diagonal. So I'll just copy it down. It becomes a lot easier to, chain the columns rather than trying to do it one by one. So now this pertains to column N. So this will pertain to column M. Sorry. So M, the next one will be an M, and O, P, Q, R, S, T, U, V, W, X, Y, Z, AA, AB, AC, AD, AE, AF, AG. H. So you notice that the last column will be AG. Or this matrix called last column is AG. So what I've got is, if you just look at any one value, I go to formulas, and if I go to trace precedence, you see what I'm going to do. I'm getting you this diagonal element. The diagonal element. So I assembled all the diagonal elements, and these are the HIIs. I'm interested in this. Okay, these are the HIIs. Okay, so now you must understand how the hat matrix is done. Very important hat matrix, a very important statistics. And now we will find out if there are any outliers in the data. Right? Yeah. Now, let me calculate the various error. Now we have this error. Now I'll remove all of this because this is not relevant for this exercise. It could affect all the other calculations. So let us put it there. Or I'll preserve this and I'll just again calculate it so that. Okay. Okay. Now let me calculate the error. The normal error. ERR. Error is calculated as y minus y hat. Right? This is the error. Now if I want the standardized error, the formula is quite simple. It is EI divided by sigma E, which is nothing but mean square error, which you have to get it from the ANOVA. You go to the ANOVA table. This is the standardized error. So this is not exactly that. It is sigma. It is error divided by sigma E, which would make it square root. It will make it square root. Okay. Okay, so I need to fix it because it will shift. So I fix it. So this is called this standardized error. Right? This is a standardized error. And now I'm going to calculate. So how do I get the standardized error? It is a regular error divided by the square root. I will just go and recollect the formulas that we used, which we used over just as a kind of recollection. So we have done that. So it is sigma by E. So it will be E and the other one will be that. So we got this square root, and now we get the studentized R, which we call T. I'll call it studentized error or residual. So studentized residual is calculated as the same E divided by, open a bracket, square root of the mean square error. I'll fix it with the 4 into this into SQRT of 1 minus the first HII, which is obtained over here. This. Okay, 1 minus HII. So please note the formula. So it is error divided by, I can just show you that. It's right here. Yeah. Error divided by, because this is also variance which I have, which I add to 1 minus HII, which is now going to be shown over here. And I press enter. So the calculation is done. So here it is. 1 minus SAT. Right? So we've got the studentized error. I'll double click it. Okay. There you are. So you got the regular error, you got the studentized error, so you got a standardized error, and you got the studentized error. Right? Right? So now you can find out. Many things from this. Okay. Now let us take the error. Now we'll go back and we'll try to see. So all the calculations are over. Now let us go and see. Now the Cook's distance. Now how do we calculate the Cook's distance? Now the Cook's distance is calculated as 1 by P into studentized residual into H divided by 1 over HI. Right? So now we're going to calculate the Cook's distance. So Cook's distance, I'll call that here. which is calculated as Cook's distance D is calculated as, I'll just go back here, which is calculated as 1 minus P. Now P is number of parameters or number of parameters. So number of parameters are here 1, 2, 3, 4, 5. So Cook's distance is 1 by P 1 divided by 5 into, open a bracket, studentized residual squared. Studentized 1 minus P, I forgot my equals over there, equals 1 minus P into studentized residual squared. Studentized residual squared. 1 by P into studentized residual squared into H divided by 1 by H into H into H divided by, I'll put 1 minus H here itself, otherwise you could have done here 1 minus HII. This whole thing I can put into a bracket for completeness. Okay, this is the Cook's D. Okay, so please see, Cook's D is calculated like that. Cook's D is 1 by P into studentized residual squared into H divided by 1 minus H. Okay, now admittedly mysterious, but it gives you the Cook's distance. Okay, we will come to the interpretation later. Now we'll calculate. Now the leverage is calculated for each variable. The leverage is calculated for each variable, so we will not worry about difference. Yeah? So we have calculated the Cook's distance. Okay, then we, yeah. So you can calculate. There's a calculating formula. So diffits is calculated as, you could try this also. Diffits is calculated as Rij. Rij is the R student residual, is the where T is the ith student residual. Now, where T is the ith studentized residual. So this we will think about later. I will now go to the interpretation. Yeah. So the studentized residual So the different residuals have different variances, and since HI is within the largest HI, those with the largest HI gives you the unusual Xis has the smallest SEs. So these are the rules. So DI value near or larger than 1 are good indicators of influential cases. So let us examine that. Now let us take a particular variable and let us take this value and make it by mistake. Let us take this decimal out from there and put it over here and make it a big, deliberately make it a big value, right? So I'm just trying to demonstrate this. I don't know why that didn't work. So maybe instead of this, can I just do a 25? So I'll increase this to 25. Yeah, just I think too large. See 25. God, where does this go away? So the independent student is error, where is that? They're just because it's all formula. So everything changes, including the regression coefficient. The student dies residual. I just want to see what goes wrong. No, nothing's affected. I'll have to just see why. What is this formula? I don't know why this formula changes. Square root of 1 minus. Student is rather this. Oh, this whole thing comes in the denominator. You should be careful. Yeah, let me just put a bracket here and close that bracket here. Okay, now try to manipulate this to 25 and find out what happened. Why these values change, I'm really not sure why that changed, because the other term